Hey, Dr. Clark, and this is our second video on Green's theorem. In this video, we're going to learn how to do a few more example problems using Green's theorem. The first one is finding area with Green's theorem. Now, this is kind of an interesting problem. What you should know is that area you can find by doing a double integral over a region of the one function, dA. Right? So integrating 1 over a region gives you the area. That's, of course, because if you have some region R and then you put a constant height 1 on it, you get sort of a birthday cake. But if the height is 1, then the volume is equal to the area times 1. And this integral will give you the volume, so therefore it'll give you the area of the region. Now, how does that help us with Green's theorem, though? So this is kind of a cool problem. So the ellipse given here, that's not a great ellipse, but here would be A and B. So this would be an ellipse with axis radius of A and B here on the x and y axis respectively. It's actually a hard problem to do with a double integral. So what we're going to do is turn this, using Green's theorem, into a line integral. Okay? And so the line integral would be of a vector field f dotted with n ds. So but what is f? Well, remember, what Green's theorem says is the 1 should be the divergence of f should equal 1 in this case. Right? That's how this works. The divergence of the vector field should equal the function if Green's theorem is going to work. So I just need any vector field f that will have a divergence of 1. Well, how about the vector field x0? If I take the divergence of that vector field, I'll take the partial derivative with respect to x and get 1, and the partial derivative of 0 with respect to y, that'll be 0. Okay, so there's a vector field, x comma 0, has a divergence of 1, and therefore this flux integral right here, the flux of that vector field out of the boundary of an ellipse will equal the area of the ellipse inside because I've picked the exact vector field f to have a divergence of 1. So it's just a really cute little application of finding area using a flux integral. So how do you actually work this out? Well, now we have f. We need our r of t that's going to parameterize that ellipse. Well, what we'll do is we'll pick a cosine of t, b sine of t. That will give us an ellipse, at least for t's between 0 and 2 pi. And now we're just going to end up with a line integral there. So we'll have a line integral 0 to 2 pi. And we'll take our vector field f, which is x0. We will dot that with the normal vector field, or with the normal vector, and then ds here. Well, this isn't quite right. We probably should keep everything over the curve here. And then what we need to do is turn this into an integral with respect to t that we actually can compute. So x is a cosine of t, so that's going to be a cosine of t right there, and that's going to be 0. Now we need the normal vector to this ellipse. So what is the normal vector? Well, if r is parameterizing it, then what we want is we want y prime negative x prime, right? That will be the unit, or not the unit vector, but the normal vector that points out. And so what's that going to be? Y is b sine of t, so y prime would be b cosine of t. And x is a cosine of t. X prime would be negative a sine of t, so negative x prime would be a sine of t. And so n ds here should be equal to b cosine of t comma a, I ran out of room here, b cosine of t comma a sine of t dt. And remember, this really is a unit normal vector times a length, but now we've put the length inside the vector dt. So this nds is equal to that dt. Once we do that dot product, we end up with just an integral to compute. It looks like ab cosine squared of t plus 0 dt. That integral is a standard half angle integral, so 1 plus cosine 2t all over 2 dt. Antiderivative is going to be ab times 1/2 of t plus sine of 2t over 4, evaluated from 0 to 2 pi. And when you get that, you're going to get ab times 1/2 times 2 pi plus 0 minus 0 plus 0. And that's going to simplify out to be pi ab. So there you go. The area of an ellipse with a and b as your sort of radiuses or whatever is pi ab. And if a and b are r, then you get pi r squared, the regular area formula for a circle. So an elliptical formula is pi ab. That's kind of a cute little formula you can get, and it comes out of a nice application of Green's theorem using just the right choice of the vector field f so that the divergence is 1. And you can do this for any shape, actually. If you want the area of a shape, you can just take the vector field x0, go around the outside of it, and compute the area. And when we were talking about that planimeter earlier, this is essentially the exact idea that is happening there. Okay, I'll do one more example here of a not simply connected region. I'm going to show you the region here. The region is this inside of this annulus, basically. And so we're going to get a little flux going out there and a little flux going out there. So normally you'd have to do, to get the total flux, you'd have to do not 1 but 2 line integrals. 1 to get the outward flux there, and then 1 to get the outward flux there. But what we're going to do is hot swap that for a single divergence integral, which will give us the total net outward flux by computing the divergence over that annular region. Okay, so essentially the flux is going to equal really C1 of f dot n ds plus C2 f dot n ds, where you've got sort of C1 here and C2, those two circles. But we're going to use Green's theorem to turn that into a single double integral over the region of the divergence of the vector field f, dA. In this case, the vector field f is given, so we can compute the divergence of that vector field. We take the x derivative of the x component, well, that's just y squared, and we add it to the y derivative of the y component, and that would be x squared. So the divergence is x squared plus y squared. And I think you might notice that x squared plus y squared in polar coordinates is r squared. So I'm going to switch to polar coordinates right here. I'm going to say the divergence is r squared. R dr d theta would be polar coordinates. And what is this region in polar coordinates? Well, it's a circle radius 1 to 2, so the r is going to go from 1 to 2, and the theta is going to go from 0 to 2 pi. So that's just a really nice r from 0, or not from 0, but from 1 to 2, and theta from 0 to 2 pi. And now I can compute that integral. Let's see, we'll integrate the r's. That's r cubed, so I'm going to get r to the 4 over 4, evaluated from 1 to 2, d theta. Plug in 2 at 16 over 4 is 4, so I get 4 minus 1/4. And I have to integrate that from 0 to 2 pi d theta. Well, that's just going to give me, let's see, 15/4 theta from 0 to 2 pi. And that's going to give me 15 pi over 2 would be the final answer. So And that's a positive number, which makes sense because we see a lot of outward flux here, a lot of outward flux, a lot of outward flux. There's some negative inward flux here, but the value of it is quite a bit smaller. So I'm thinking that 15 pi over 2 is positive because we're seeing all of that positive outward flux. All right, so there's a couple examples how to do some Green's theorem problems, switching between the divergence integrals over a region or the line integrals, and you can see sometimes you want to do it one way and sometimes you want to do it the other way. In the next video, we'll see some circulation versions of Green's theorem.